Hey everyone, and welcome to our mini symposium on Julia for high performance computing at JuliaCon 2022. My name is Michael, and I'm from HLRS at the University of Stuttgart. And together with William Godoy, I will lead through this mini symposium today. We have a very tight schedule with eight lightning talks, so I'll ask everyone, please try to stick to your allotted times. For everyone listening here, the schedule is available on the pre-talks website. And I will hand over now to William, who will give a short introduction to this mini symposium.
Thank you, Michael. Thanks, everyone. So my name is William Godoy. I'm a research scientist staff here at Oak Ridge National Lab. So today we're going to talk about a little bit why we want to organize this mini symposium, right? As you know, Frontier has been deployed fastest exascale system in the world currently, and we are very interested in using Julia at these scales. So in these 2 hours, you're going to have information about the current landscape for Julia and HPC. We're going to provide an informative venue. This is the whole reason we are motivated to do this, because the people behind these efforts are willing to share, and this is going to be very important, because without a community, this is not going to be possible. And hopefully, this will be very helpful to the audience, and having this will actually make us grow as a community. So this is a good opportunity for us to rethink how we do computing. We see this, at those who work with supercomputing, that scientific programming is really hard, especially the scales we're targeting. And software becomes our specialized equipment when we want to do science. And we need to know enough about the science, the domain, and also about the hardware. This is nothing new to this audience. So one of my favorite quotes is from Bacchus on Forten, because he was trying to solve not only a technical problem, but a economical problem. So this is how I see Julia, how it approaches it, especially when the landscape has changed 2022. Have things like AI, machine learning workflows, which is a completely different world from the more traditional HPC. Let me go to the next. So trying to make a case for Julia around here, and within our community, putting on my DOE hat, we are thinking about how to take a different approach as co-design, especially since these are heavily multidisciplinary problems that have become very complex. So Julia is trying to be a good balance between having something that is fast but not as complex, and trying to position it in this quadrant, right? So it's a very interesting language that we want to explore more. The community and our efforts here at ORNL, can be summarized in these slides. I don't want to go through all this, but this is something that it's really, really important, caught my eye. I'm very happy to share with all of our collaborators here. This is a multidisciplinary effort. We're working towards, establishing the foundations for Julia in HPC. It's probably the last frontier for the language. And we have, external and internal engagements. As part of our preliminary exploratory work, we did some runs comparing as naturally as it comes Julia with CE and alternatives like Python, NumPy, CUDA. So we want to try to explore where we are and what the gaps mean, and for this community, and how we can come together and try to address these problems as we use Julia for science. Similarly, we're trying to test things on Crusher. Part of our job is to work as a community. For example, I give credit to Ludovic, because we're trying to test one of his frameworks on our systems and make sure things can work smoothly. Some final thoughts: that we ran a local workshop at ORNL, and the impression was, out of the 101 responses, is that 92 want to learn about it. So it's still very new for the large majority, even though they're vibrant communities. So the interest and momentum are very real. That's a message I want to share with this community. Some final thought. I just want to say thank you to all the speakers for coming here. We have a very exciting agenda, and ideally, we want to be able to answer the question, right? Like, what is the return of investment for somebody willing to use Julia for their science at these scales? And once again, I'm very proud of the people, this community. I have a lot of fun, and I just want to acknowledge my sponsors. And please enjoy the rest of the mini symposium. Thank you.
Thank you very much, William, for the introduction. So without further ado, I would like to start with the first speaker. The first presentation is going to be by Samuel Omlin from CSCS. He has actually pre-recorded a video that we're going to play right now. And there are different ways in which you can ask questions. I will just show them at the banner below. You have the ability to use Pigeonhole. You can also ask on the Julia Slack in the HPC channel or on the JuliaCon Discord in the green channel. Hi, Sam. Welcome to our mini symposium, and I'm looking forward to your talk.
Hi, thanks. Welcome to my talk on the scalability of the Julia GPU stack. I'm Samuel Omlin, computational scientist and responsible for Julia computing at the Swiss National Supercomputing Center, ETH Zurich, and my co-authors are Ludovic Räss and Ivan Utkin, also from ETH Zurich. In high-performance computing nowadays, people often mention the 3 Ps: performance, portability, and productivity. More specifically, one may understand the 3 Ps as scalable performance, performance portability, and productivity. Everybody agrees it is a challenge. In this talk, we will present you one part of our solution to this challenge. More precisely, in order to perform large-scale high-performance computing, we have addressed the questions noted on the right here. Now in this talk, I'll focus on distributed parallelization, in particular on the scalability of the GPU stack. Of course, I also need to give you our answer to the question about the programming languages. Now, of course, to everybody's surprise, this is Julia. How do we achieve an efficient distributed parallelization that addresses the 3 Ps? Our solution is automatic distributed parallelization of architecture-agnostic code. As the color shows, automatic is for productivity, distributed parallelization for scalable performance, and architecture-agnostic code for portability. Note that throughout the presentation, you'll see these colors, and they will always refer to the 3 Ps. The package Implicit Global Grid does exactly that for stencil-based applications. I presented you already the 3P challenge we want to address in this talk. Now I will discuss automatic distributed parallelization of architecture-agnostic code with Julia and its primary requirements on MPI.jl and the Julia GPU packages. I'll use implicit global grid as an example. In the end, I'll report results and finish with conclusions. Implicit global grid is designed for domain scientists. It renders the distributed parallelization of stencil-based GPU and CPU applications on a regular staggered grid nearly trivial. It relies on MPI.jl, CUDA.jl, and AMDGPU.jl, and supports CUDA and ROCm-aware MPI. Moreover, it is seamlessly interoperable with MPI.jl and of course also with parallel stencil.jl. Finally, it uses implicit domain decomposition. What do I mean with implicit domain decomposition? On the left you can see the global grid, and on the right how it looks like decomposed with halo regions. Now most people start on the left with the global grid and get to the local grids by decomposing it. We do just the other way around. We say how many times we want to have a local problem in each dimension, and that way we create implicitly the global grid. Here's an example of automatic distributed parallelization of architecture agnostic code using implicit global grid. We initialize the global grid by passing the size of the local grid, an XIY, to initial init global grid. Then an XG and then YG let us retrieve the size of the global grid. We add update halo and finalize the global grid to the code, and we're done. Note that we introduce only point-to-point communication at every iteration with neighboring processes, meaning that it can scale a priori to any number of processes. First, note that array H can be an array, C array or rock array. The right communication routines will be called with multiple dispatch. Second, note there is no need for explicitly send receive buffer or CUDA stream ROCm queue allocations. Automatic allocation happens at the first update halo call. Then what is allocated is reused until finalized global grid. Reallocation of more memory happens only if update halo is called with bigger arrays or more arrays. Now let's have a look at the requirement of update halo on MPI.jl and the Julia GPU stack. So for communication via host, we rely on its support for page locking of host memory, for maximal device host transfer speed, and mapping of host memory to device for access from GPU kernel, and CUDA ROCm provided optimized async routines, for example, for 3D device host memory copies. Then, for communication with RDMA, as you see on the right, we rely on its support for RDM and RDMA-enabled CUDA ROCm over MPI, of course, and abstract device arrays as arguments for MPI.jl routines. To achieve optimum scaling, we need to be able to hide computation behind communication. Now, implicit grid is compatible with parallel stencils feature to do that in an automatic fashion. This is how it's done. It splits the computation simply into computations of a boundary region and of inner points and launches them on two different streams. And then as soon as the boundary region computations have finished, it starts the halo update, which will be performed simultaneously with the ongoing computation of the inner points. Now here is what we rely on for hiding communication behind computation. For communication via host, we rely on its support for non-blocking high priority streams, for overlapping access of host send receive buffers with computations, and non-blocking, of course, CUDA ROCm provided optimized async regions, for example, for 3D device hostman copies. Then on the right side, you see for communication via RDMA, we rely on its support for non-blocking high priority streams, for overlapping access of device send receive buffers with computations, and of course also non-blocking RDMA data transfer routines in the MPI library itself. Here you can see the timelines of the communication and computation routines of a run with CUDA MPI on a single node with 4 NVIDIA Tesla V100 GPUs. They're connected with NVLink, so that means the MPI communication is going through NVLink here. Here we zoom into 3 or let's say 2.5 iterations, and you can see that the communication related routines in purple overlap the computation routines in green. Now the communication part will be much longer for runs with more than one compute node, of course. Results and conclusions. Here we see the parallel efficiency of a Julia 3D poroviscoelastic two-phase flow solver in yellow and the CUDA C solver it was ported from in blue. So far we run the Julia code only with up to 1024 GPUs. We got a parallel efficiency greater than 95%, thanks a great part to parallel stencil's hide communication feature. We achieved similarly good results with a 3D nonlinear diffusion solver and a 3D viscoelastic Stokes solver. We obtained over 96% parallel efficiency on test ups to over 2000 GPUs. I'll keep the conclusion very short. We showed that using Julia, MPI.jl and the GPU packages, we could successfully implement distributed parallelization that enables great scalability and addresses the 3P challenge. As this talk is part of a mini symposium, I will conclude with a little side note. End of last year, we had a Julia GPU-HPC course at CSCS. Instructors were Tim Besard and myself. And you can find all the relevant information material and an edited video on the following link. Thanks a lot for your attention.
So thank you very much for this video, Sam. We will directly follow this talk with another talk by Simon Byrne from Caltech, who is going to be talking about the MPI.jl package. you will still be able to ask questions also to Sam. He'll try to answer via Pigeonhole or Slack or Discord. But after this talk, we'll also have 5 minutes for the two speakers to have some live Q&A. So Simon, I'm trying to load up your slides.
Oh, I can share my screen if that's easy. Maybe not, actually. Yeah, if you get my slides, that might be easier.
I think that should do it. So
yeah, that works.
Yeah. Please go ahead.
Well, thank you for the opportunity. So I'm I guess somehow became the primary maintainer of MPI.jl. And this was intended to be MPI.jl 1.0, but we're not quite there, mainly due to, I think, being caution and ensuring everything works before we release it. To introduce myself, I'm the lead software engineer in the CliMA project at Caltech. And yeah, I've been sort of working on MPI.jl since I started there about 3 years ago. Next slide, thanks. So MPI.jl, I'll give a bit of background. As the name suggests, it provides Julia bindings to the message passing interface, which is, I guess, the lingua franca of communication and parallelism on HPC systems. So it started by Lucas Wilcox back in July 2012, so not, within a year after Julia was sort of released. Since then, it's had about 60 contributors. So what seems to happen is that people pick it up for a project and modify it, add some new features, and then someone else, the next person picks it up, and somehow I'm the latest person in that chain of maintainers, although there's also been in the recent times, there's been a large number of contributors who I'm very appreciative. So the overall interface is very similar to I guess the Python one, MPI for Pi, which, full credit, is a fantastic library as well. And the overall idea is it tries to be similar to the C API, but with some Julia niceties. So the principal one being we try and do a bunch of other things to handle buffer length and data types. We generate custom data types and operators on the fly as needed. And we can use Julia exceptions rather than sort of propagating error codes. I guess those are the principal ones. The core idea is that at the moment, we exposed most commonly used functions, but if you look at sort of the proportion of total functions that are used, there's probably still a proportion. There's still only a small part. So if there's something missing, pull requests are always welcome. And if you want a sort of a longer introduction, we have a JuliaCon 2020 talk, and there's also a proceedings paper from that talk, which gives a sort of a nice introduction into sort of the overall ideas behind that. To cover what's changed recently, most of the work since then has been consistency and interface cleanup. So to make as the library had evolved and people had added different things, people had different ideas, and so we tried to make a large number of those consistent. So consistent naming, use of mutation, the suffix, exclamation suffix, and we also added some keyword arguments to make some of the interfaces a bit clearer, which a lot of the MPI interfaces just provide integers, so you have to remember the order of the integers that get applied, so it makes it easier to use keyword arguments there. We've added a lot more APIs, so there's, as people have added, which various, particularly the one-sided communication ones have been much improved. So, thank you to the contributors for those. And there's been a lot of bug fixes and work, and I think actually probably the most work has gone to doing bug fixes and workarounds for various implementations and backend libraries and hardware. So I will say that the UCX library is possibly the bane of my existence, simply due to how it sort of things it does. It's a sort of a common backend library used by a lot of MPI implementations that is under development, but often we find holes in it that perhaps people were otherwise unaware of. There's also been a fair bit of work on the better docs and examples, though more always welcome. And I do plan to release version 0.20 soon, which is effectively going to be the pre-release for version 1.0. So there won't be, the idea is once we get version 0.20 released, it will be the final version, be close to no more breaking changes. So I thank you to everyone who's put up with my occasional breaking releases. I appreciate your patience. So I think I'll give a quick overview of some of the nice features, I think, particularly that have come about since then. So GPU support, the GPU support MPI consists of basically allowing to use direct MPI communication between GPU devices. So you don't have to buffer through local memory, host memory. And the core principle in MPI is that it uses the same functions. And so instead of passing a sort of a pointer to a host device, you pass a CUDA pointer or a pointer in some sort of GPU device. The key thing is it requires some sort of GPU-aware implementation, and the implementation itself may require specific hardware. That's up to you. And so that requires us to use an external MPI library rather than the pre-built ones we currently use. We provide by default. At the moment, we support both CUDA, which added actually quite a few years ago and has been widely used, CUDA.jl arrays. And more recently, we now have support for ROC arrays and AMDGPU package. And it's, so many thanks to the people who have worked on those. This still has some rough edges. And part of this is simply because the GPU-aware extensions aren't really standardized in any as part of MPI. So there's no way to actually query what features are available. Not all functions are generally supported. Most common ones are, but but again, there's no way to query which functions are supported. So there's some intricacies in the sense that you're using asynchronous devices. So CUDA.jl, for example, uses per thread streams. These should be then manually synchronized before you do any communication. So it's not quite a drop-in replacement, depending on how you're writing work. And then I guess my biggest complaint here is that reusing these MPI functions, although it makes it easy, perhaps on the user, it does impose significant technical limitations on the MPI libraries themselves. And so they need to jump through a lot of hoops. And this is probably the single cause of the most complications that we have, is the libraries having to work around these technical limitations of reusing the same functions. So I'll leave it at that. Before I could probably spend the 10 minutes complaining about this, but I won't. So thank you. Thanks. The other big change you will see is the use of MPI preferences, this MPI preferences package. So this is the changes the mechanism of how you select an MPI binary. So the problem is that every cluster will typically have their own MPI implementation that they want you to use, or possibly even more than one, depending on the cluster. And the big problem with MPI is that there's no standard application binary interface. So that means the type, sizes, and the constants are not standardized across implementations. Previously, we used the PKG build mechanism, which you had to configure using environment, set a bunch of environment variables, and then call PKG build. This made it very brittle when you had to switch between implementations. It required a full rebuild. And it also mean that if you try it wasn't really feasible, or it was very difficult for sort of sysadmins to make it so that you configure it in a way that could be used for all MPI versions, because it was that PKG build is tied to a specific version of MPI.jl. So MPI preferences uses a different approach. It uses the new preferences system. So MPI preferences is simply a very lightweight package that lets you select the MPI implementation. So you can select between either the pre-built JLL libraries that we provide, so MPIC or OpenMPI, or Microsoft MPI Windows, or the new MPI trampoline package, which is a MPI wrapper shim, which is by Reuther, and is also may become standard in the future. Or it also provides the system MPI. So I'll give an example here. So you do your system MPI, and there are keyword options, but it will generally detect quite reliably what the ABI is used, and the path of the library and the launcher and those sorts of things. So this allows for setting the preferences system is quite nice because it allows you to set system-wide settings by modifying the Julia load path, and it plays nice with the precompile cache, and then downstream write binaries. As I said, are a work in progress. It also works, the other recent change, which is not so obvious, but it lets you now works with MPI profilers. So MPI.jl, we've modified it so it now uses global SQLs, which lets you now use profilers and debuggers, which are based on LD preload, to intercept MPI calls. So as an example, so some of these are very expensive and typically come with a cost tied to licenses are tied to costs themselves, but the NVIDIA Nsight Systems is a free version. Although it's originally developed for CUDA profiling, it works quite well without a GPU and has MPI hooks. So here's an example here. And I'll give a quick plug for the MPI.jl package, which I just recently created, which lets you do custom instrumentation. So you can tag, instrument your own code, and also lets you provide hooks into the Julia garbage collector. So if you're having garbage collection problems, it will let you instrument that. Okay, so I've got a few slides just into what I wish could be better. So what I'm unhappy with the package. Printing is something I've never really liked. And a large chunk of this is how MPI launches themselves merge standard input and standard output and standard error from each process. And so you'll always see this when it's a perennial source of complaint, and somehow Julia seems much worse than other libraries. I think basically due to how Julia buffering works, makes it does seem much worse than say Python when I've compared some of the comparisons. So a large chunk of it is I don't have a good solution, but I would be very open to anyone who has ideas on this. And I will say stack traces especially are quite bad.
Simon, you have about 1 minute left.
Okay, that's fine. 2 more slides. Next slide, then. The other big complaint is the lack of interactivity. So the Julia REPL is one of its nicest features. And the problem is we can't run a REPL from inside an MPI launcher. So you can't do MPI launch, MPI exec Julia, because basically the buffering, again, these launchers intercept, control their standard input and standard output, and buffer it is generally incompatible. And try as I might, what's called singleton MPI, which is basically means you launch MPI outside the launcher. Although that works for a single process, the features to sort of connect or spawn more processes, as far as I've tried, have never worked in any implementation that I've tried. So that's very unfortunate. It makes it difficult to make full use of Julia's interactivity. The only workarounds I've seen so far is this quite nice TMPI package, which is basically an MPI launcher that launches TMUX sessions and then multiplex the keyboard to all the processes. And so, I mean, obviously this only works on a single node, but is quite useful. It can be quite useful for debugging MPI. It's quite useful for debugging, but not really much beyond that. And then the other one people have had some success with is MPI cluster managers. And so this is basically a distributed.jl worker that lets you start the MPI launcher. The problem is then the main process is not part of the MPI session. And again, it's not ideal because then the main process can't use MPI communication with the focus. And the last slide, I'll just finish on. And my main complaint here is that is how to integrate with the Julia task system. So as I said, MPI is primarily used in an asynchronous mode. And so that means you obviously want wait. But what Julia wait does is lets you switch to other tasks while the tasks are blocking. But MPI wait will get stuck in a C call. And so we yet to come up with a good solution to this as well. MPI doesn't provide any callback or notification system that we can make use of here. So at the moment, the best alternative is to use a spin lock or block a single hardware thread there. Okay, thank you. That was my.
All right, thank you very much, Simon. Also, thank you very much again, Sam, for your presentation. We have now some time to answer some questions here in the stream.
Yes, can you hear me? So please feel free to ask your question and pigeonhole the link. So we have one for, let's start with Simon. What are the biggest issues that you have experienced when using Julia and MPI on larger scales? I/O issues related to the Julia depot, maybe?
Yeah, to be honest, I haven't tried huge scales to see what's a problem. And a large, there is a significant overhead in starting up. I think there has been some work by Valentin and others to deal with this issue. And I'm probably not the best person to ask, since I think others have probably run it at much larger scales. But yeah.
Yeah, I could answer our experience with that. So indeed, at the beginning, when we had Julia and all the packages installed on the GPS, the home, on the GPS file system, then indeed we had quite some problem in scaling it up to like more than 1,000 GPUs. Now we have it on the Lustre file system. We have it on Scratch, all the packages automatically. And so we have not seen any problem with that so far. And we have made tests up to 2,000 something GPUs.
Great, thank you. I have another question, actually one for Sam. Like, are there any efforts to extend parallel stencil implicit global grid to 4D?
Well, let's say the basic model is CUDA, and this is built in a way that with indexes for 3 dimensions, right? But like with CUDA in CUDA-C, whatever, doesn't mean that you can only do stuff in 3 dimensions. Then a second part of the answer is we have now support for cell arrays. This is going to be released very soon. Cell arrays are like arrays which have, instead of simple scalars in their cells, they can have little arrays or structs in there. And when I say little arrays or structs, they're logical arrays or structs. So the layout in the memory is totally independent of the type in there. And there you can, in that way, you can have more than 3 dimensions very easily.
Right. Well, I want to thank both of you for this first part. There's more questions on Pigeonhole. Also, I want to remind that feel free to reach out to the participants. We're, great community. And yeah, let's keep moving on with the program. Thank you very much. Those great thoughts.
Thank you.
Thanks.
Yes, thank you very much, you two. The next talk is going to be by Tim Besard from Julia Computing, and it's going to be about CUDA.jl, update on new features and developments. It's actually a pre-recorded video, but as with the other videos, feel free to answer questions. Tim is here, and he'll try to answer them either in text or later live.
Hi, I'm Tim. I work at Julia Computing on CUDA.jl and other GPU backends. In the next 10 minutes, I'll give short updates on the features and developments in CUDA.jl since my previous talk at JuliaCon 2021. If you have a look at the code, quite a lot has changed actually. Excluding non-interesting changes like header updates and artifacts, there's more than 10,000 lines of code added over the course of more than 600 commits. Importantly, this was done by 45 unique contributors, of which 25 were new to the project, so that's great. To summarize these changes in a 10-minute overview, I first focus on array programming features and then on changes related to kernel programming. So one first important array-related change is the support for unified memory in CUDA.jl 3.4. If you've used CUDA.jl in the last year or so, you may have seen that we have introduced a new type parameter that keeps track of the underlying buffer type, which defaults to a regular buffer type, a regular device buffer, as you can see here. It's possible to use different values for this parameter, which will result in the CUArray constructor allocating a different kind of buffer. For example, a unified buffer that's automatically shared between the CPU and the GPU. And for these kind of buffers, we can specialize the copy-to function so that it directly copies between CPU memory, which results in significant performance improvements. Of course, the memory will still be transferred to the GPU when you use it in a kernel, but that happens lazily, so this might be beneficial to your application. And if you want to play with this, we have added a convenience keyword argument to the Q function. Do note that this is not a stable API, and it might disappear once we figure out a better way that we can support across all of the GPU backends, because, for example, Metal.jl also bets heavily on unified memory. Another memory-related improvement is the ability to copy arrays between devices. For example, we can now allocate an array on one device, switch to another, where we also allocate an array, and then directly copy between those arrays without having to stage through the GPU, as was required previously. Or you could use unified memory, but being able to copy it directly is also beneficial. And since CUDA.jl 3.8, that's done automatically. Even better, if your system has support for peer-to-peer communication between GPUs, like over the PCIe bus or using NVLink, will automatically use that instead. So this is also a better performance option than staging through the CPU or using unified memory. We also worked on support for ISBITS union types. So the Q-array array type generally only supports element types that are so-called bits types. Those are primitive types that can be represented by plain memory without pointers. And starting in CUDA.jl 3.3, we now also support storing unions of bits types contiguously, similarly to how the CPU array implements this optimization. And this is mainly interesting to support nothing or missing values. And generally, we expect that our API seamlessly supports such values. However, it's possible that you run into type unstable code by using these values, and as a result, there might still be some issues lurking. So file some issues if you run into any of those. Another area that's been greatly improved is sparse arrays. Over the last year, there's been a whole bunch of improvements by Roger Luo, and our sparse array types are now in a much better shape than they were last year. However, we are always still bound by the functionality that's supported by the QSparse library by NVIDIA, which, for example, is limited to simple C types. And to work around that restriction, we also started looking into implementing our own sparse array operations natively in Julia. And we started with one of the most commonly used operations in Julia, namely broadcast. So let's compare and have a look at the performance on the CPU and on the GPU. So on the CPU, we start by allocating two sparse matrices, random sparse matrices. So the sparsity patterns of Cx and Cy are different. And then if we add them together using broadcast, that takes about 1 millisecond. Now, starting with CUDA.jl 3.9, we can also do so on the GPU. So we upload these matrices to either a compressed row or a compressed column format, and then we just perform a broadcast. And as you can see, it's significantly faster. On my GPU, it took 150 microseconds compared to the 1 millisecond on the CPU. And the output is still sparse. So even though the sparsity pattern of both inputs are different, we merge them together and we still return a sparse output. There's a couple of restrictions. One is, for example, that we only support broadcast between sparse arrays of the same type. So you cannot add a CSC with a CSR matrix. And we also currently do not support this for COO or BSR sparse matrices. However, support for broadcast should make it possible to implement a whole bunch of other array operations. So hopefully by next JuliaCon, our sparse array abstraction will become much more full-featured. For those of you who write your own kernels, we also have a couple of improvements to show. For example, it's now possible to write code that depends on the device capability without having to write multiple versions of your kernel. As an example, here I have a kernel that branches on the compute capability. Note that the SV is just a version number, but it's GPU compatible, so it's a simple version number. Now, if you look at the generated code, you can see that this branch has been completely optimized away, and we just store the value 1. And if I switch to an older GPU with compute capability 3.5, which is the other side of the branch, you can see that we automatically generate other code storing the value 2. Again, this happens fully automatically. There's no need to switch between different kernel implementations. CUDA.jl just recognizes that you switch to a different device, and it generates new code. This functionality is only supported for two functions. One is the compute capability function to query the compute capability, and the other one is to query the PTX ISA version. And we added this to CUDA.jl in order to improve our atomics, because atomic functions often depend on the hardware generation in terms of which types they are supported. So using this, we greatly improved a lot about our atomic support. One improvement is that the API is now clearly split into two levels. First, we have the low-level API, where operations map directly onto hardware-accelerated intrinsics. So these functions are low-level, they're prefixed by the atomic underscore, and they only take pointers, not arrays. What's also low-level about this API is that you, as a user, need to take care that your hardware supports the operation in question, or you will run into compilation errors. The exact requirements are always in the doc strings of these functions, but for example, if you want to use int16, float16, or float64, you need to have sufficiently recent devices. Then we also have the high-level APIs implemented on top of this, and this is the CUDA.addAtomic macro. This is a different macro from base.addAtomic, and the two are currently fully distinct. But it's much more convenient because you can convenient than the low-level API in CUDA.jl, that is, because you can use it with arrays. You don't have to use pointers. And since CUDA.jl 3.4, it also automatically falls back to a generic compare and swap loop when the operation or the data type isn't supported. That means that with the high-level Atomic API, you generally do not have to think about hardware support. And finally, we also improved automatic installation of CUDA and now automatically upgrade the CUDA driver when possible. For example, here I'm on a system where the NVIDIA driver that's installed only supports CUDA 11.6, but we automatically upgraded the driver to 11.7. This only applies to the current process, so you don't need any administrative privileges. And as such, it's very interesting on, say, clusters where it's typically hard to upgrade the NVIDIA driver, yet you still want to benefit from the latest and greatest CUDA features. Note that this is only supported on enterprise hardware, meaning not GeForce hardware, but it requires Quadro hardware. And this is a restriction by NVIDIA itself. And that's it for a quick overview. If you want to be kept in the loop, please subscribe to the blog at JuliaGPU.org, where we periodically post about new releases of CUDA.jl and the other GPU backends. And all of the features and updates that I described in this talk have also been released previously in blog posts on JuliaGPU.org. Thanks.
All right. That was Tim on CUDA.jl. Thank you very much. The next video, the next talk is going to be, again, a pre-recorded video by Julian Samaroo from MIT. And he's going to talk about AMDGPU.jl, so the AMD counterpart to what we just saw. After that talk, there will be, again, the opportunity for some live Q&A. So stay tuned.
Hi everyone, my name is Julian Samaroo. I work at MIT's Julia Lab and spend half of my time there, give or take, working on AMDGPU.jl. This package, as many of you may know, allows executing pure Julia code on AMD GPUs, similar to how CUDA.jl enables this for NVIDIA GPUs. AMD GPU has come a long way over the past few years since its inception and has gained a lot of capabilities and integrations with various libraries. In this talk, I'm going to discuss where AMDGPU.jl stands today and what changes I expect to occur over the next few years. AMDGPU.jl has come a long way over the past year. Since this time last year, we've built and deployed ROCm components as JLLs, we started passing the entire GPU arrays test suite, and we've generally kept up with changes in our upstream dependencies. Many bugs have been squashed, and quite a few features have been added. We've also very recently landed a large refactor of the codebase, which simplifies a lot of things that made development annoying, along with renaming things to be less confusing for users. Not all of the changes have been technical in nature either. We've also had an influx of active AMD GPU users, partly due to the onlining of various AMD GPU-powered supercomputers, including Frontier, Lumi, and Satonix. These users have been instrumental in uncovering bugs and sharp corners, as well as unexpected performance traps, and have submitted a number of PRs to fix them. Let's take a look at some of the changes that have happened since last year in more detail. JLLs. Nobody wants to have to build code from source if you're not planning on making changes to that source. I feel the same way, and so I spent some time getting the core pieces of the ROCm stack built as JLLs for all those users who don't have a working ROCm install on their system. By default, AMDGPU.jl will automatically pull in the necessary components of ROCm 4.2 as JLLs, allowing for a mostly pain-free experience. The only component we can't ship as a JLL is the AMD GPU Linux kernel module, but most distributions are shipping it by default these days, so that's usually not something users need to deal with either. Unfortunately, building all of the ROCm libraries correctly is a pain, so not everything is available as JLLs. Most importantly, in terms of libraries which aren't strictly necessary, We only have JLLs for RNG functionality, but are missing BLOS, FFT, Linear Solver, and Deep Learning Library JLLs. I'm thankfully in contact with some engineers from AMD who have been very helpful with looking at building these missing libraries, so I expect that we can sort this out over the next few months. Test coverage. A strong test suite is key to success when dealing with a complicated interplay of compilers, runtimes, and devices. As far as testing GPU array operations goes, the GPU arrays test suite is something of a conformance test suite for GPU-powered array computing in Julia. 1 year ago, AMDGPU was having trouble passing many of the tests in that test suite for various reasons. Thanks to a large effort by co-maintainer Valentin Charavi, today we can boast full conformance with the test suite. This means that the ROC array should work in the same way that people have come to expect of the Q array, and should work with many kinds of generic array libraries correctly. MPI support. Many users of AMDGPU.jl have access to powerful clusters and want to do distributed computing across multiple compute nodes in their cluster. The de facto way to do this is MPI. CUDA.jl has had MPI support for quite some time, so it was obvious that AMDGPU also needed similar support. Thanks to the concerted work of a number of our users, especially Ludovic Räss and Simon Byrne, we now have support for ROCm-aware OpenMPI. This support opens the doors to distributed GPU computation in a manner that many researchers are familiar with and for which many packages already know how to leverage. Future directions. AMD GPU development isn't slowing down by any measure. In fact, the onlining of various new AMD-powered supercomputers is greatly hastening the development of AMD GPU and bringing in many new users. Let's briefly look at what new and existing users have to look forward to as we go through 2022 and 2023. Examples. While AMD GPU has a variety of simple unit tests that somewhat double as documentation of how to use the available features, it would greatly help users if we had a larger set of examples that show how to do things with AMD GPU. Showing off the various math intrinsics, host call, asynchronous task launch, and synchronization, MPI integration, and more should be added as examples to the repository. We can also test these examples to make sure they always work as expected. Library integrations. Most of the power of Julia's GPU arrays are in how they magically work with many high-level libraries that users employ to solve their computational problems. CUDA.jl users have enjoyed excellent integrations for some time now, so making sure that AMD GPU users get the same benefits is important to ensuring our users are productive and happy. To that end, there are many libraries in the ecosystem that still need AMD GPU support. These include the SciML ecosystem packages, Flux and Lux, Implicit Global Grid, and many other packages that users rely on. Doing this will take some assistance from the ecosystem, but I'm confident that users will start trying to make these packages work with AMD GPU once they get access to AMD hardware. Profiling and debugging. While something of a long shot, it's my desire to see better integrated support for profiling and debugging in AMD GPU. This would entail directly interfacing with ROCm's ROC Tracer and ROC Debug API libraries to access information on GPU state, and a way to expose this to users that is intuitive for beginners and powerful enough for advanced users. While it would be a potentially large undertaking, the result could significantly improve how productive AMD GPU users can be. There has been a lot of progress in AMDGPU.jl this past year, and a lot more is planned for this coming year. I hope that those of you who have access to AMD hardware will give AMDGPU.jl a try and help me get it up to speed and integrated into Julia's ecosystem. Thanks so much for listening.
All right. Thank you, Julian, for your presentation. We now have also some time to answer questions. Let me see. We have Tim here. Do we have Julian here? No, but he's online and he can answer your questions also via text.
So yeah, we have one question for Tim. It says, how can broadcast be faster than GPU and sparse matrix?
Yeah, I responded to that question because it wasn't entirely clear to me what the question was about. So going on a limb here, what the question may be about, the reason that GPU broadcast is faster because we can still parallelize across either the rows or the columns in the case of prospectively compressed row or compressed column layout. So, and then within each GPU thread, we iterate the compressed indices. So there's less parallelization opportunity than with a dense matrix, but there's still some significant opportunity to use the GPU's threads to parallelize and get some speed up compared to the CPU. Assuming, again, that was the intention of the question, but I'll monitor the pigeon link question in case the user wants clarification.
Great, thanks. I have another question. Does CUDA.jl support TensorFlow 32 precision format?
Yes, so there's a twofold answer for that. On the one hand, TensorFlow 32 can be automatically supported by using appropriate cuBLAS API calls. And we do so automatically when you set the CUDA math mode to allow the slightly less precision you get by using TF32. If you don't do that, then we'll never use the TensorFlow implementations. If you set the math mode, we'll do so, but only for a select number of API calls. And the most important one is, of course, matrix multiplication. If you want your own kernels to use WMMA with TensorFlow 32, there's currently a PR open by Karsten Bauer, who's also here on the call. That hasn't been merged yet, so if you're interested, please give it a try and have a look at that PR. I also linked to it in the pigeonhole question.
Thank you. That's great. Michael, there's a question for Julian. I don't know if he's online or he's able to take it pigeonhole, or we can move on.
I don't see him here on the stream. Maybe he can answer it on Pigeonhole.
All right. Yeah. So we can move on, I guess.
I think there's actually a single other question. What's the status of the debugging tools for CUDA.jl and AMDGPU.jl? So let me quickly chime in on that. Because it's interesting in that we do support emitting debug information for CUDA kernels, but the problem is that there's lots of bugs in the PTX assembler. So out of being careful, we disable that by default. So if you need to debug some kernels using CUDA GDB, please get in touch, because I can explain how you enable the debug mode and what the specific requirements are in order to debug Julia kernels.
Thank you very much, Tim. I actually asked that question. That's why I was running over, but that's great. I appreciate that.
All right. I've also added Valentin to the stream now from MIT. He also has maybe some answers on that question.
Yeah, for AMD GPU, the debugging support works surprisingly well. It can be sometimes a chore to set up, but I managed to get ROCm GDB working and to live debug code on the device to figure out a segfault, and I got a better experience than I was used from CUDA, because I got actual line information for all of my errors. The bigger issue I have with the AMD toolchain right now, and that's a complaint to AMD directly, is that the setup for the profiler and everything else is quite annoying, and GDB support needs their custom kernel because they have not upstreamed the kernel support yet.
Just a follow-up, Bounce. This is for ROCm version 5.2, 5.1?
It might have been 4.5.
Okay.
Or 5.0. I think it was 4.5 when I last tried.
Okay. Thank you.
We still have time for some more questions.
Maybe Bounty might know. This one says, what about graphics and compute interoperability in AMD GPU?
Yeah, I think Julian answered that in text.
Okay.
The support in the underlying libraries is there, and it is basically just an amount of engineering effort, but we haven't done that on the AMDGPU.jl side. So that's hopefully something to get to. If you're interested in working on that, maybe reach out.
Great. And I just want to add quickly that we tested CUDA.jl on the A100s here and AMD GPU on the MI250X on Crashers. So they're looking good. So congrats, guys. Great job.
I have a question. Maybe Tim can also shed some light on this. So some people who I talked to about using Julia for HPC, they asked me, how do you find the time to work on these packages? Like, what's your driving motivation behind this? Because I mean, usually people, put in time because they like working on something or because they need to work on this. So I was wondering if you can maybe shed some light on this. I mean, what made you put in so much effort into maintaining such a great package?
Yeah, in my case, I'm lucky enough to work at Julia Computing where I can just do this full time. It used to be much more tricky because I also did this as part of my PhD, where I was looking into the necessary compiler interfaces to make this possible. And that basically resulted in GPU-Compiler.jl, which is now the basis of many of these backends. And actually implementing a GPU backend was, of course, a prime use case for said interfaces. But nowadays, I'm doing this full-time because you can use CUDA.jl in Julia Hub, which is one of the main products of Julia Computing. So it's important for the company to have good GPU acceleration and good GPU support with that main product.
And to maybe expand on this, from coming from a similar path, I started working on all of these open source packages because I wanted to do research, and so it wasn't able to do what I wanted to do at the time, and so I started using Julia. I started using OpenCL.gl. Suddenly, I became one of the co-maintainers of OpenCL.gl, and over time, the amount of work I spent doing research diminished, and the time I spent on maintenance and working on Julia packages increased rapidly. And similarly to Tim, I'm now fortunate enough that I do this basically as part of my job at MIT.
Okay, thank you very much for sharing. I mean, I personally I can relate to both what you guys have already said. Usually it's you start pulling on one string. You say, hey, this sounds interesting. Maybe we should give this a try. Maybe we should take this nice library and which is already parallel and try to use it from Julia, and then you see, oh, but then I maybe need to add another thing to it and maybe need another dependency, and sooner rather than later you are the co-maintainer of 5 different packages, and now people are coming to you for questions. So I can see how you can get roped in quite easily, especially in the Julia HPC community. All right. Is there another question, William? Otherwise, maybe we can go on.
No, yeah, and just as a reminder, we have a BOF as well on the topic on HPC, so on Thursday. So that will be also a good opportunity to, extend the conversation.
That's a great reminder. We will show the link to the BOF as well at the end of this session, but maybe we can show it a little bit during the conversation as well. But well, for now, thank you again, Julian, Tim, and Valentin for the presentations and answering the questions. We will move on now with the next 2 talks. They're from Albert Reuther from MIT and Johannes Blaschke at NERSC, and they're sort of bringing the supercomputer operators perspective to this mini symposium. So I would like to welcome Albert. Hi, Albert.
Hi, Michael.
I'm really happy to have you here to bring your perspective also to this mini symposium, to not just hear from the users or the package developers, but also to hear from the people who have to deal with the users. So let me share your slides. I hope either you can click them yourself. Otherwise, just let me know and I will, click through them for you.
So I don't think I have clickability, but so
All
let's
right.
go on to the next slide. I thought I'd first give a little bit background on MIT and MIT Lincoln Laboratory. I think everybody knows MIT. Our previous couple of speakers are from there, but MIT also runs a laboratory for national science called Lincoln Laboratory. And the Lincoln Laboratory Supercomputing Center runs clusters in both of those realms. And we, on both sites, rapid prototyping is really a key part to what we do. System engineering, understanding the art of the possible, data analysis, building AI models and testing them on different data sets. It's all part of the kind of the same workflow that we've enabled. It's not to say that we don't support traditional supercomputing as well, like large computational fluid dynamics models and electromagnetics models and things like that. But our focus is really on enabling users that need interactivity and on-demand capability. So let's go to the next slide. And so from the ground up, 20 years ago, we started building what's now the Lincoln Supercomputing Center and the MIT SuperCloud to enable interactivity. And I'm sharing this because this flows really well into what a lot of us do with Julia. And our users, both on campus and at Lincoln Laboratory, are taking advantage of this interactivity as a primary basis for using our system. We have ability to use dynamic Jupyter notebooks, dynamic databases online, interactive nodes that we are running small and large jobs with, as well as a few other capabilities. I'll get to the end and how we've integrated that with Julia. But our primary focus is to enable users to get online and running on a supercomputer quickly, and then enabling them to, when they then want to run big, run lots of jobs, giving them an easy transition path to that, using Julia and other languages. So let's go on to the next slide. Not surprisingly, like many supercomputing centers, we offer a lot of different software packages. So you see the traditional C, C++, MPI, Fortran, a variety of third-party and commercial codes, machine learning frameworks, but we do support kind of as our first-class citizens, so to speak, Julia, MATLAB, Octave, R, and Python. And that's because we find that those high productivity languages is usually the entry point for those rapid prototyping users to kind of get their ideas into code, run through their data sets, train their models, AI models quickly, and then eventually maybe they will run it at a much larger scale using some sort of batch queuing engine. But the first thing is, does it work? Do my ideas work? Can I run it at a reasonably large scale in these high productivity languages? So let's focus on Julia, obviously. Let's talk about Julia. Let's go on to the next slide. So something that I'm not sure how unique it is, but something that we feel very strongly about in terms of enabling these rapid prototyping users is that Julia is installed, multiple versions of Julia are installed right from the get-go, and that they don't have to do any installation themselves to get the Julia prompt. What it also means from the system's point of view is that we have faster launch times because we're installing Julia locally, multiple versions locally on every single node. Our flagship system has 2,000 nodes. It also means that the command line, Julia command line, is much more responsive, and a nice side benefit is that the central file system sees less load from the interaction of the command line or of the execution on that central file system. As you can see with the graphic, my terminal graphic there on the right, we have currently 5 different versions of Julia available, and we use the common Linux environment modules to enable users to load those. As you can see, we have a lot of other packages available. Those Anaconda packages are for Python and R, but we're not talking about that right now. We also enable users, obviously, to modify and customize their Julia environment using the .julia directory in their home directory. so that they're not hemmed in to what we install as our rather expansive package set with Julia. I won't say that we have everything but the kitchen sink, but it is quite a well outfitted kitchen of Julia packages that we do install natively as the latest version for that version of Julia. And we will soon, no worries, we will soon have 1.7 available. It's just not there quite yet. Let's go on to the next slide. There are three primary ways that users can interactively work with Julia on our systems. One obviously that you saw on the last slide was the interactive session command line. We also have a lot of users that use Jupyter notebooks. And what we have somewhat uniquely done, though it is now available in other capabilities like Open On Demand, is that we run Jupyter notebooks on compute nodes, and that we do port forwarding of that web interface through a web portal for security reasons. You see a screenshot of that here on the right. We also have interfacing capability for VS Code and other such APIs or development environments. On the next slide, you see another build of this with me running some code, some Julia code within the Jupyter notebook. This is part of that rapid onboarding of our users to be able to use Julia. We encourage them to use the Jupyter notebooks in order to get their code running, to debug and stuff like that. And then we have very extensive online help to help them take what they've been interacting with and turn it into a batch job. And on that note, let's go to this next slide here. A couple of tools that I want to highlight for you that is a little beyond what usually users have. We noticed that our users were often using doing kind of a MapReduce sort of mentality, but they weren't doing it for Java. They were doing it in MATLAB. They were doing it in Julia, in Python, and in R. And so one of the tools that we have, the paper link is on the bottom there. We created our own MapReduce capability that overlays the two-level Java array scheduling for the mapping and reduce stages of bulk synchronous parallel and Monte Carlo simulations, such that the user just has to plug in what the code is that they're running, what data sets they want to run, the input data that they want to run against it, and then execute many instances of that. They can also then do a reduce step to collate the results off of that to produce gathered results from that. Another capability that we have is interactive databases, online interactive databases that run on single or multiple nodes on the cluster. And we have a capability, D4M.jl, which enables the dynamic distributed dimensional data model. It's a framework for doing graph analysis and other database-like analysis in a sparse linear algebra context. And that can run standalone or with integrated databases like MariaDB and Accumulo. Papers for that are down below. I'm not going to spend too much more words on that, but hopefully I've given you some insight into how we manage and enable our rapid prototyping users on MIT SuperCloud and Lincoln Laboratories Supercomputing Center, with both the installation as well as the tools to make users productive, usually within hours, hopefully not days or months. So that's all I've got for you, and I'll be online for questions.
Thank you very much, Albert. This was a very interesting talk for me. I'm sure that other people will have questions as well. For now, we have the second talk in this two-talk package, which is by Johannes Blaschke from NERSC. And he's going to talk about supporting Julia users on the Cori and Perlmutter systems. Welcome, Johannes. Thank you very much for joining us. And please, the floor is yours.
Oh, thank you, Michael. I I was a little bit surprised to see that Albert was almost on the machine room floor or something. So it's anyway. So NERSC is a supercomputing center that, like Lincoln Lab, has a very diverse user, very diverse set of users. And here you see a shot of our building. So we are situated at Lawrence Berkeley National Lab, and we provide the HPC resources for all DOE, for all projects that receive DOE Office of Science funding and need HPC resources. So I don't think I can click. Thank you. So what that means is that we are hosting at the moment about 900 projects, and based on a count from 2020, you can see that this is a mission compute facility. So we are really doing compute services that are relevant to the whole of the DOE Office of Science mission, and it creates a very diverse set of projects. Here's a census of the different project areas. And then if we go to the next slide, what we see is in 2020, we had about 8,000 users that were using the machine. And now it's actually closer to 9,000 users. What I really like to point out is that if you add up undergrad, grad, and postdocs, then you get about 55%. So more than half of our users are actually early career scientists. Also, we are not, even though we are operated and funded by the Department of Energy, most of our users are actually from universities. Next slide, please. And so in 2020, all of those 8,000 users, they essentially used 9 billion core hours, and they cited us, acknowledged us in about 1,800 publications. This number is actually nowadays closer to 2,000, but I don't have official numbers for you at this point. Anyway, moving on to the next slide. We are currently running 2 supercomputers. Cori was commissioned in 2016. It is our production supercomputer. It is a CPU-only machine with about 12,000 nodes. At the end of last year, we started commissioning Perlmutter, which is going to be our next production supercomputer. Phase 1 is currently available to general users. It has 1,500 GPU accelerated nodes, and we are now finishing off putting in 3,000 more nodes that are CPU only. That would be Perlmutter phase 2. And once that's complete, Cori will go offline, and then we will run Perlmutter for the next 5 or so years. What you can also see here is it's important that you don't just provide the compute, but you have to provide everything around it. Our data center operates a variety of optimized file systems, and everything is held together using a high-speed network. This network isn't just for like general networking, but we design it also to provide tailored services like data transfer nodes, gateways. Attached to all of that is a cluster that hosts our Jupyter Lab instance and workflow nodes, so that we can also start transitioning users to more complicated workflows rather than just running compute. Next slide, please. Just to summarize, what I want everyone to take away from this is that NERSC users come with vast variety of experience with HPC. They can be HPC experts in computing sciences, or they can be just domain scientists that need to use a supercomputer for the first time in order to make their science happen. Our hardware is heterogeneous in order to accommodate a lot of these different science use cases, and it will remain heterogeneous. And also looking to the future, we find that high-profile engagements will increasingly involve cross-facility workflows. So those are things like live data processing from an experiment. You can imagine maybe analyzing the plasma dynamics in a fusion reactor. And so that creates two needs. The first one is that we need to have high productivity, high performance glue code. And the second one is we need to have portable workflow performance. And this needs to be the whole workflow, including data transfers and other edge services. So next slide, please. Thank you. In terms of the need number one, our objective at NERSC is to establish high productivity, high performance languages. And I think Julia is a really good candidate for those. Python is developing as sort of the de facto one. But if we contrast, for example, the call time for just calling a C function from Python versus Julia, you can see that you're paying a significant overhead switching between Python and C. And Julia doesn't have this overhead. And that makes Julia much more flexible, right? You don't have to avoid switching layers. If your science requires you to call highly optimized C code, then and then make decisions on the fly, then Julia can accommodate that. So next slide, please. So before we started supporting Julia officially at NERSC, we conducted surveys to see how much interest there would be in the community. NERSC has a long history of actually supporting Julia. Back in 2017, actually, the Celeste code was one of the hallmark codes that used the whole of Cori, and that news even made it into HPC Wire. And so in 2020, we conducted a survey, and we found that about 74% of users that responded to the surveys said that they did not use Julia. However, when we also asked them, do you plan to use it in the future? About half of them either said yes or were undecided. And of those, about half wanted to use Julia at NERSC. So there was going to be a lot of interest in Julia in the future. So next slide, please. So we started developing modules that enable Julia at NERSC. And as will become clear in the next few slides, we use different levels of support. We split up the modules to have settings and then actually precompiled packages. And so the settings module is just there to make sure that when someone goes, for example, installs MPI.jl, that it'll automate that the system environment is set up so that it will automatically build against Cray Ampage. And then further down, if a user doesn't really want to build their own Julia environment, then we have a Julia module with precompiled packages already in the depot path. Next slide, please. And so in addition to providing modules, we monitor their usage. And back in 2021, we noticed that the number of Julia users, unique Julia users, had grown to about 138. Actually, now the count is closer to 299. Next slide, please. And we are also monitoring which versions of Julia get loaded. And you can see that Julia 1.4 is in decline, and then there was a peak for 1.6, and now 1.7 seems to be rising. And so it seems that Julia users really like the latest version of Julia. And so this is an important consequence for data center management because we need to find a way to keep up with our own software release cycle with the user requirements. And that also motivates creating an environment that allows Julia power users to build their own environments. I didn't mention this, but also, of course, we support Julia in Jupyter Lab. And final slide, yeah. Ongoing work is in the area of increasing the fine-grained monitoring of our users in order to understand what packages they are actually using in order to include that into the precompiled packages. We have a pipeline for Python already that's published The citation is there, and we are looking to solve some technical issues in order to implement that in Julia. The other thing is that we have already completed, and we're continuing to make sure that we have production level support for Julia. So that means optimizing Julia performance and including that in center operations. And future research is being conducted around workflow portability, and also how non-standard, non-MPI.jl style use cases can actually interact with the workflow managers and the resource schedulers that we have at NERSC in order to facilitate large-scale operations. And then finally, I want to also make a plug for our postdoc program. It's called NESAP, and if anyone is interested in joining us as a postdoc or an HPC engineer, I will post some links and also check out our website for open jobs. Thank you very much.
Thank you very much, Johannes, for this very interesting talk. I'm also adding back Albert to the conversation, who did the first talk on Julia for HPC from a system operator's perspective. So do we have some questions, William?
We do, actually. One question is, since you're representing very well the facilities here, what are the most critical issues for Julia users at the facilities?
Do you want to go first, Albert?
I think what we see on our team is maybe twofold. One of them is being up to date on packages. Some folks want to be on the very, very bleeding edge, and those are often the easy users to work with. But then there's others who just aren't really sure what to use and what to install. That's part of why we have those modules pre-built for them. The other piece to it is just understanding how they can parallelize. I think a lot of our users on campus in particular, but also at Lincoln, they understand their serial code really well, but then educating them, training them how to think in parallel, and even just bulk synchronous parallel is often a mind shift, a leap forward for them. To think about it, think about many experiments and Monte Carlo experiments as well. So that educating them, helping them turn the corner to go parallel is often a big step forward for them.
I also want to add that my interactions with Julia users has been that they're usually braver to try non-classical workflow patterns. My favorite one are task-based parallelism built around things like MPI Cluster Manager. And they exercise the software stack and the system in a very unique way, because vendors, they kind of imagine you come with a Fortran code, you've compiled with our compiler wrapper, and then someone comes along and is like, yeah, I want to add an MPI rank and I want to drop it again. I actually see that as an opportunity. I think future workflows will actually have to go in that direction. So I enjoy these problems, but they are difficult to solve. And some of the technical problems around, talking to Slurm via PMI2 can be incredibly hard because none of this is documented. And no one anticipated 5 years ago that it needs to be documented. I also want to point out that a lot of these things are also problems in the Python world. So Dask is a good example in Python. And so far I've found that the Julia way of doing things in terms of package management is better, right? So if someone loads the Julia settings module at NERSC, and they go add MPI.jl, it will build correctly. If they just go pip install MPI for Pi without any modifications, it won't work. And so from a management perspective, it's nice that with Julia, I can control the system environment to prevent the users that might not know what they're doing to shoot themselves in the foot, right?
Sure. And I'll move on, Michael, or do we have time for a quick question? You're muted.
I think we have time for one quick question.
Yeah, so there's another one related to what Albert was saying about Jupyter. I mean, it's widely supported and deployed, for interactive computing and HPC centers. Any interest for Pluto as a Julia native alternative among people using Julia?
I'll take it back to the team, possibly. We have that portal capability that we have is very extensible, and so much so that we even have instructions for users if they want to create their own portal front end, work with our portal to forward web traffic to their laptop. I've done it myself, so it's quite extensible, quite easy to use. So, but yeah, I'll take it back to the team and see what they say. It probably is an easy lift to add Pluto to it. Thank you.
Thank you. Thanks, all. All right. Should we move on, Michael? Or?
Yeah, sounds good.
All right. So next, it's Michael here. You're going to be presenting our work. Let me actually. Do you want to share it?
Yes. So thank you very much, William. In my talk, I will be speaking a little bit about running Julia code in parallel with MPI and sharing some of the lessons learned. So the target audience for this is mostly people who are coming from HPC, and they just started playing with Julia and want to figure out what kind of things will I encounter when I try to run a classic Julia code in parallel, or those folks who maybe have already some experience with Julia and now want to go parallel and find out what kind of challenges they might have to face. So the work I'm presenting here was actually mostly conducted by two of my students, Lars Christmann and Niklas Nea, who are also from HLRS. So the outset for this endeavor was the question, does it scale? So we had a Julia code available for computational fluid dynamics. It's called Trixie.jl. We already had it parallelized with MPI and have used it on workstations, on laptops. And now we also have a supercomputer available, Hawk at HLRS. And the question we want to answer is, so how easy is it to, to just go naively and, try to scale things up on an actual production machine? So first of all, what is Trixie? Trixie is an adaptive numerical simulation framework written in Julia. Its focus is on high-order methods for computational fluid dynamics, and it has a hybrid parallelization with MPI and multithreading, and multithreading is mostly provided by the polyester package. The kind of simulations we're looking at, this is an example. It's a simulation of a wind tunnel at supersonic speeds. It's with a front-facing step. You see, this is the density plot. So there are some shocks forming here, detached shock here. Then you have some shock interaction. You have some instabilities forming here. And you can also see that we have these little black lines forming around the shocks that are actually mesh lines and which are adaptively, refining the mesh towards the shock. So this is the kind of problems we're looking at. There's actually a video for this particular simulation if you're interested. Now, the system we've been using are Hawk and Vulkan. These are two computers installed at HLRS at the University of Stuttgart in Germany. Hawk is a capability system with roughly 700,000 cores. And Vulkan is more geared towards industry user with 10 to 20,000 cores. And on both systems, we have Julia available as a compute module. So the first question you might encounter when you start using Julia on such a system is where to put the Julia folder. Now, the Julia depot path specifies the location where package files are located, the pre-compilation files are stored. So typically it's just in your home directory, but doesn't make sense if you look at the supercomputer system. And I think Sam has already mentioned it. If you put it in your home directory, which in our case is accessed via the NFS file system, Julia actually crashed when using more than 2,000 MPI ranks. So that was not nice, of course. On the other hand, if you put it on the parallel file system, in our case it's Lustre, because there's so many small files, we actually encountered some issues like slow package updates. And depending on the restrictions of your supercomputing center, you might run into quota limits, actually. So what are the lessons learned here? Well, figure out the optimal depot location before doing any parallel runs. And this might really depend on the machine where you're running on, as well as the application you're actually using. Then some observations for MPI and multi-threading in general. We observed there's generally a high memory usage of the Julia runtime. So just for loading Trixie.jl and ordinary ETH.jl, after compilation and garbage collection, we still have a 500 megabyte memory footprint, which is quite high. So hybrid parallelization with MPI plus multi-threading seems to be what you should be doing. However, here also we sometimes faced problems that seem to be system dependent, also dependent on the MPI version, on the MPI implementation used. So stuff that works locally or on your local workstation might not work on your supercomputer. So you have to check this out. And we also found that using non-standard MPI implementations, for example, vendor-specific MPI implementations, are not as well supported like the big two OpenMPI and MPIJ. So the lessons learned here for us were you should really test which MPI implementation to use, which one is the best one on your system, and verify that multi-threading works as expected before doing any major parallel runs. Next, when you start using Julia on a supercomputer, you will have to, if you want to maximize your performance, you will have to replace some of the JLL provided binary with system binaries. So for example, for MPI.jl, the process is straightforward. You can just tell the system to use a different MPI implementation, the one installed on your supercomputer. But in that case, you also might need to change the MPI implementation for other packages that use MPI. And then you cannot rely on this very convenient JLL system anymore, but you have to switch out a lot of binaries with system binaries. Similarly, if you're relying on packages that have C bindings, you might have to regenerate those because if the MPI ABI changes, you cannot use the old one anymore. For example, that's the case with P4.jl currently. The lessons learned here are, first of all, document all your setup procedures for your users and yourself, being it whether you're a package manager or a system operator. And as it was mentioned already before in the talk by Simon, have a look at MPI Trampoline, which aims to solve some or maybe all of these problems related to different MPI implementations. The next point is certainly one of the bigger ones and not unfamiliar to those who have used Julia in serial. The runtime overhead due to code loading and compilation. Code loading times actually can increase when you do run Julia simulations in parallel due to the increased pressure on the file system. Albert had already reported that for this particular reason, they actually do sometimes have some packages stored in a node local storage system. Also, code compilation itself can be slower in parallel. And I'm sharing some results here that we obtained on Hawk. You can see in this plot for one rank, so the very left part of the plot, the blue curve, that's package loading plus first compilation time is at roughly 60 seconds. And if you increase the number of processes to 128, that time increases to almost 120 seconds. So the good news here is that it does not increase beyond that. So once you have saturated your node and you go to multi-nodes, this times, at least in our experience, did not increase anymore. But as usual, when you do parallel computing, the general rule applies. Any non-parallel operations such as code loading or compilation increase your computational cost. So the lessons learned here are try to use the package compiler to create a custom JuliaSys image, which will cut down both on the loading and on the compilation times. And you might want to try to use the HPC spindle tool, which allows you to avoid the I/O bottleneck by basically parallelizing access to small files. And finally, there's some restrictions when trying to do interactive computing. Simon has already mentioned that. At the moment, there's no inherent MPI support for the REPL. And given the long load compilation times, parallel development with Julia and MPI is not fun, I would say. And parallel debugging, is even less so. So there's one workaround. You can use the TMPI tool, which is quite nice, but it only works with a small number of MPI ranks. And of course, the other lesson learned is you have to be patient at the moment. Finally, I want to show some very, very early results from scaling Trixie on Hawk. Please be aware that this is really very much work in progress. So some of these numbers were just obtained maybe 2 weeks ago. So we have quite good scalability from 1 rank up to 32 MPI ranks. And if we go further than that, the scalability is still acceptable until 64 MPI ranks. Now, I know this is not an HPC scaling. I mean, we're not looking at the 1,000 core range here. But at least from what we can see, and we've done also some larger runs already, the parallel performance of Julia is similar to what we expect from C++ and Fortran codes. And for me, that's a very good message. So finally, to conclude, running Julia code in parallel with MPI works. There are some additional challenges compared to traditional HPC languages. Most of them are related to the fact that the tool chain for using and developing with Julia in parallel is not as mature yet as with other languages. And the question whether Julia with MPI is the right tool for your personal HPC needs, well, you need to, it depends. As usual, I would say as a rule of thumb, at least from our experience, if you have less than 100 cores or MPI ranks, you're golden. There are no issues there. If you use up to 1,000 cores, then most of it should still work out of the box. There might be some issues, but nothing that cannot be fixed. If you go beyond 1,000, well, then you go into the realm where you have to put in real work, but that's not so much different from other languages either. And the final lesson learned here is that you should really interact with the great Julia for HPC community. There are a lot of people out there who are working on this, who have tried things before, and either to get some knowledge from them or to not feel alone with your issues, it's a good idea to reach out. So thank you very much for your interest, and yeah, I'm looking forward to your questions.
Thank you very much, Michael. Appreciate it, and it's been a pleasure collaborating with you and organizing the mini symposium. It's very informative. So
thank you very much.
Yeah, absolutely. Next, it's Ludovic Räss. He's from ETH Zurich, another collaborator. Are you ready, Ludovic? Can you share?
Yeah, sure. I shared Windows, so you should have it in the streams. Yeah, here we go. So, well, yeah, thank you for organizing this mini symposium on Julia HPC, and thanks also for inviting me. Yeah, so today I'm gonna talk about, yeah, somehow on the application side, and well, our efforts to basically, yeah, integrate Julia as a HPC tool to leverage GPU computing in parallel for earth science application. This is a collaborative work with folks from Germany, Switzerland, and MIT, and we just recently got a project, GPU for Geo, funded where we look at frontier GPU multiphysics solver with application to both ice flow dynamics and geodynamics mostly. So maybe short intro on those applications. So those applications, they actually share quite some common things, although they may look different. So in both cases, actually, we're interested in solving Stokes equation, incompressible Stokes equation mostly, for either the solid earth science or like ice flow motion. There are little differences, like for ice flow modeling, there are like challenges related to boundary condition, basal sliding, etc. While in geodynamics, there are other challenges, for example, related to basically processes that would like govern how viscosity behaves and how deformation and nonlinearity interact together. So the goal of that project is to propose software tools which provide a way forward in two domains, so ice flow modeling and geodynamics, but leveraging a powerful emerging paradigm in HPC, which is massively parallel iterative solver, and HPC. And in particular here, we made a project we advertised a project that we use HPC with Julia to leverage GPUs. And so, why GPUs? In a nutshell, GPUs, they kind of populate the biggest supercomputer nowadays. And for example, just a couple of weeks ago, Frontier, first exascale machine, which is basically runs the AMD GPU. But here in Switzerland, we also have a new supercomputer called Alps that will be hosting the latest generation NVIDIA GPUs. And what makes GPUs attractive from our point of view is that we have, we solve partial differential equation on these GPUs, and our codes, unless one uses fancy techniques that are not that efficient actually, they're mostly memory bound. In that sense, what really is key is that the devices on which we solve our equation and run our codes, they should have like the highest possible memory bandwidth. And they're like GPUs, they really outperform CPUs. Like nowadays, modern GPUs, they have like over an order of magnitude higher memory bandwidth compared to CPUs. And it's actually much easier to leverage the peak memory throughput on GPUs. So you may ask the question, like, why did we go for using Julia and GPUs? Well, there's a kind of there are twofold answers. So, first thing is the two-language problem, but I guess that by now everyone is more or less familiar with that, in Julia, it's very easy to, have the same code where we can do prototyping and development, and then production runs with the same code, because, Julia has many advantages along those lines. But maybe one thing that I can highlight is that basically using packages we developed, for example, Stencil, with Julia, we can really get at the hardware limit. So in that sense, we can really, here it's an example for a nonlinear diffusion solver, we can really run at about over 90% of the peak memory throughput of the hardware. And that makes it super interesting. On the other hand, for example, with implicit global grid that Sam was presenting a bit earlier, we can also scale up our single GPU solvers now on multiple GPU. And for example, for the same 3D nonlinear diffusion, we can show that we lose less than 2% in parallel efficiency while going from 1 to over 2,000 GPUs in a week scaling on a PID-stand computer. That's one part of the story. Now, the other part of the story is if you want to have good kind of scalable and parallel software, you also need a good solver, and you need also a good algorithm. So the implementation is one side, but the algorithm should also be suited to actually perform well and scale well. And the algorithm we now push forward since a couple of years, and that is pretty mature, is called the accelerated pseudo-transient method. And the idea, you see it here in the little code snippet. So that code snippets, if you make abstraction of the red lines, it's basically solving explicit diffusion equation. And we can use this explicit time integration as pseudo time and use it to reduce the residual, basically, solve to a steady state. The thing one can do is one can add little history on the rate of change and turn diffusion process into a wave equation and then dump that wave equation. And we can use this now to try to smooth this random noise. And what we see is like naive Picard type of iteration. We would kind of reduce an order, half an order of magnitude over 2000 iteration. And like the accelerated pseudo-transient approach will just bring you down to like machine, kind of close to machine precision in the same 2000 iteration. And with this approach, basically, we could solve nonlinear diffusion or viscoelastic Stokes problems in 3D on like resolution that are about 5000 cube in like about 10 minutes for diffusion and about a couple of hours, 7 hours for the Stokes problem. And like we got the paper that, if you're interested, that got accepted just yesterday. So that's all about Julia GPU in that paper. So have a look, it's open source. So where we use those solvers and where we apply this tool, the Julia GPU development we do. So one thing is on the geodynamic side. So we're interested in kind of complex rheology, so visco, elastoplastic, deforming rocks. And here we model, for example, in 3D, brittle failures or shear bendings when you squeeze that block in 3D on multiple GPUs. And you see that on this little plot on the left, that basically the GPU solver in 2D here, that's the plot is for 2D, the GPU solver with the iterative algorithm outperforms easily the CPU-based implementation, which use like a, let's say, direct iterative scheme, so standard Krylov type of algorithm. Another thing that I'm personally interested in is glaciology and ice flow, and basically we use one of the outcome of the GPU4Geo project, and current work I'm doing is to try to basically resolve ice motion and complex multiphysics processes related to ice flow on glaciers. And here is a stress field distribution on the Rhone Glacier in the Swiss Alps, and one sees that there is like stress concentration at the base, which may be related to shear heating, frictional heating, and which make the glacier slide. Now, it was already mentioned today, well, we do some work to try to get the, our GPU stack to scale on AMD GPUs, and for that we made modification to include AMD GPU support to implicit global grid, and like added also modification to MPI.jl, and a big shout out here to all the folks who helped, also Julian Samaroo. And well, as kind of nice proof of concept, we got our little benchmark to run thanks to William on Crusher system at Oak Ridge. And well, this used ROCm aware MPI with implicit global grid on 8 MI250X GPUs, and well, kind of solving diffusion equation here. But if you're interested, you can look into the codes and how to are on my GitHub repo. Yeah, so related to the project, there are a couple of packages we developed, like with support, for example, from Sam and the whole team, and also with support from Valentine, the MIT folks. And well, that's just a couple of those. Like the most important one, maybe regarding really HPC application. But if you're curious, we have a project thread little website where you can sneak in, and well, there's a lot of information there. That you can look up to or reach out to me if you have further questions. And well, it's not about teaching here, but it's about HPC and GPU maybe. So we will run in this year the second edition of a course, which is about solving a partial differential equation in parallel on GPUs at ETH in Zurich. And the whole course is, well, it's all done in Julia, like all the resources are in Julia. It's kind of uses all the web integration. And well, apparently students really enjoyed it, so we are like super motivated to go for the second edition. And well, as I wrote it down in the Discord chat, the philosophy for that course is, well, teach Julia, basically teach HPC and GPU in a hands-on approach, and this is only possible with Julia, I guess, for now. So that's really cool. Well, and with this, I'm at the outlook. So, well, we have the GPU for Geo project that puts a frame to push forward well, many HPC and GPU related development in Julia, and a big thanks to everyone that kind of contributes, also to Sam. What's going to happen next will further develop, well, parallel stencil and implicit global grid for sure, but we have also recent work that I presented yesterday on actually some GPU HPC optimization using AD with enzyme, and in this pseudo transient framework you can like pretty much straightforward make a joint inversion by really leveraging enzyme on GPUs, and it just worked like a couple of days ago, so we were super excited, and it scales. And yeah, well, we do some other stuff like try to explore hybrid FD and finite element things for just capturing crazy geometries, but that's more to come. So, well, thank you for your attention. And if you want to stay tuned, please, yeah, have a look at that link to our project website.
Thank you very much, Ludovic. This is great. Thanks, Michael. Actually, we have questions for both of you since you're here. One's for Michael. Could you cover briefly what are the requirements to that Julia code that is currently used and distributed to use MPI technologies?
That's actually a very good question that I'm not really the most qualified person to answer, because we actually never tried that. As far as I know, there's a MPI cluster manager that is able to do this, but maybe we can ask someone else in who might shed some more light on this. So maybe we go to the next question, and we'll see if we have someone here who can answer that.
Another question is, any experiences with package compiler to avoid this just-in-time code loading compilation related overheads?
Yeah. So, or Ludovic, do you want to answer?
Well, please go ahead. I could add something if needed.
So we did some experience with using a package compiler, and what we could see is that so with package compiler, you typically have your you set up a little script that you can run, and then package compiler will record all the code that has been loaded, all the functions that have been executed, and store all this code in a sys image. Now, what we saw when using package compiler is that it's possible to completely eliminate the time that you spend on using packages. So especially if you have a couple of heavy dependencies like Flux.jl or ORNL GPU.jl, that already helps quite a lot. And if you prepare your sys image in a proper way, you can also cut down considerably on the compilation time. We're not able to completely you will not be able to completely eliminate the compilation time unless you run the exact same simulation and store everything in your package. But just by storing all your dependencies in the sys image is already a great help, in my opinion.
Thank you. I have one for Ludovic. How difficult it is for students to learn GPU concepts using Julia, since that's part of the curricula you're teaching?
Yeah. Well, interestingly, we didn't see much friction there. Because maybe we also, as I said, like our philosophy was to really, make it like a field experience, like for people who do, like, for example, but it's a concept in earth sciences or geology. One would do, like, some people do lab work, and some other people, they like to go in the field with a hammer and do some sampling, etc. So our approach to teaching Julia HPC, or GPU HPC, sorry, with Julia is really like more hands-on. So we tried to make it very limited on the theory, but since, well, all the interactivity, I would say, of Julia, we really let them play and, well, figure out the things. And especially, for example, using parallel stencil is really one thing that helps a lot there, because it has this ability to have a single code that would run both on a single-threaded CPU, multi-threaded CPU, and then on the GPU. So they can really, well, first maybe start with some fake parallelization to just get, get some idea, and then really just try to write a little code and play with it and see how it works. And then either you can do it like this directly in the REPL, or we have also some notebooks that you can just execute and, well, see by yourself that in some cases performance is really good, in other cases performance is really bad, and yeah, and that's it. And so I guess that for now it worked, like, to try with this different approach. So instead of trying to kind of show them all the possibilities and then pick one, we rather kind of motivate one that we know that works, and at some point when they're kind of when they experienced with it and kind of could convince themselves that it works, well, then you can try all the other things that won't work or won't work as well. And with this approach, it's actually, well, we really managed to, throughout one semester, bring them from, well, basic, well, I did some Python once in my life, or I kind of turned on, or I did a little bit of, was using MATLAB or Julia for one project, to actually make them code up some, well, I don't know, some did like 3D Navier-Stokes, etc. But yeah, like, I guess that's really one of the thing, and where Julia is really important there, it really is a playground. So you don't have to teach them lengthy concept. You can just like tell them one thing and they can try it themselves and see. And I guess that's really one important point that makes life easier.
If I may add one more thing, because I just saw a question pop up on Pigeonhole, where someone asked someone essentially asked if Julia code and how the performance compares to traditional C++ and Fortran codes. And I think this is really important. I mean, what you said, Ludovic, it's very easy for students and for users in general to get to know Julia by playing around with it, and you can do this without sacrificing any of the serial performance, at least. We did some studies with Trixie, and we really pitted it against a mature Fortran code, and we saw that there is virtually no difference in performance. It really depends in the end how many hours more you spend tuning one or the other codes. So serial performance is not the reason not to use Julia. So this is one of the questions I get a lot of times from folks in the traditional HPC world, I would say. And the speed compared with the simplicity, I think that's a really great asset.
Yeah, that's a good point. Like, well, before using Julia, and so one reason we are now really also for a project switched totally to Julia and Julia plus GPU is that for the first time we tried many things. So we're doing mostly things in, well, C and CUDA, or a bit of Fortran and CUDA, but mostly C and CUDA. We had did some little libraries that would do the stuff how we want, like close to hardware limit. And then we were like really looking if there's a higher level language where one could kind of combine both. And, well, basically Julia is for the first time that you can write like super short codes, like let's say Python or MATLAB like codes, like super short, but, well, when you have to do it right, but then you can really get the same performance. Or with GPU, actually, CUDA.jl in some cases like slightly outperforms C CUDA. Same implementation, just I guess because how maybe the GPU compiler in Julia GPU does the thing, which is a bit different than what NVCC would do. But yeah, that's really new capabilities, and if one can motivate that, especially for students, then they really like it.
Yeah, thank you very much both. Michael, I'll give it back to you. We're almost done.
Yeah, we're almost done with the official part of this mini symposium. So I would like to invite back all the speakers who have presented here. And by inviting back, I mean I will just add them back to the stream. Also, some of the people who did not speak today, but who are part of the Julia for HPC community, who have been involved in pitching this mini symposium to the JuliaCon organizers. And I think everyone who's online, we have everyone here in the room. So maybe we can use these a few more minutes while there's still interest also from the audience to field some more questions. Maybe some questions on Pigeonhole or Discord that have not been answered yet. I, for once, have been asked a question, but that was already partially answered by Ludovic. So one question was, are there any scientific project with funding which rely on Julia outside of the computer science world? So, going into the application world, are there any projects? And I think, Ludovic, the GPU4Geo project qualifies as one of these projects, right?
Yeah, exactly. Well, I guess it's maybe a bit hybrid. So it's still a call that's emitted. So it's a call from the ETH, so the Technical University here in Switzerland, but together with the computing center. And it fills a gap. At least we have, I don't know for Europe, but at least in Switzerland, it filled that gap that for a long time now, regular science foundation would really prohibit or refuse funding scientific software development because, well, it was a problem solved, there is what's needed, etc. And now we see that, well, in the recent years with all, I guess also all this new data and all the processing needed, that, well, basically there's not much way around using computers to do science nowadays. They really now try to push a bit like forward again. And, well, this call is, at least for our project, is a mixture between computer science, but it needs some targeted domain science application. And yeah, and on that side, what we were also so we were a bit careful with pushing Julia too much because we were afraid that it would be somehow not appreciated as it should by maybe the review panel, because it would bring in something new that may have some resistance. And we were actually super surprised because the Julia part that we didn't put too much in the spotlight to play it safe was actually what was picked up and was really pushed forward by the panel that reviewed it. So yeah, I guess that was a super very motivating signal.
And maybe to add another part to a potential answer to this question is, despite the fact that this is the Julia HPC mini symposium and many of us represent HPC centers and we tend to go large scale to thousands of nodes and thousands of GPUs, right? There are lots of science projects which also run on supercomputers, which are not super large scale, not worth mentioning in the sense that they break records of any kind. However, they are real, right? And there are quite a bunch that I know that use Julia, and they are funded. They are not funded for Julia, of course, right? Because it's a science project, and essentially they don't care which language you use to implement your algorithm in. But also speaking personally, I've used Julia as a physicist on clusters, right? So if we expand the question in that regard, I don't know if it was meant in that regard, right? Then there are quite a number of codes that I could name that use Julia and run on HPC clusters.
There is one project I would like to highlight, that is the Seismics PSAP Center here at MIT, and that's multi-scale material simulations. So it's an application development. It is using Julia, but and so we do HPC research as part of it, but the driving factor is an application.
And also at NERSC, based on the tickets that come in, it's clear that in certain spaces, like in think in cosmology is one of those spaces where you start to see sort of little groups develop, and so I guess what I'm saying is our power users, our Julia power users, usually come from like this one group over there. And then I noticed that we have, I don't want to name names because I haven't gotten permission to name names, but we have some power users, they come from this area, and I can sort of see little clusters pop up somewhere else. And so that's the reason why I think it's also important for HPC centers to monitor which codes run as part of what projects. Tickets are a great way of seeing who has what questions, but maybe someone's using it just happily and doesn't need to ask questions. And I still need to know, how are they using Julia, and how can we make that support better?
I think that's a very good point, and one of the recurring questions that I also get from my colleagues, for example, in Stuttgart, is who are the users? Like, who are the users who do use Julia for HPC? What kind of codes do they use? Is it something that is typically embarrassingly parallel, or are there users who do complex simulations that would, 10 years ago be done with C++ code? And I think this is also where the Julia for HPC community can still, improve, where we can still improve by, putting these codes that are already existed, that are available, that are used, and make them more prominent, and make sure that other people see, okay, there is precedence, and people are using it.
Maybe that's a good, intro to the community slide that we have prepared, Michael, right? Since you speak to the community, right? It would be great to hear back from the community.
That's a good point. Yes, thank you very much, Carsten. Maybe you can introduce it yourself.
Oh yeah, sure. Okay, so first of all, obviously we all hope that you like today's mini symposium, right? And we obviously would also like to hear from you. That you get in touch with us, the community. For example, share such codes that Michael just addressed. Maybe there are some that we are not aware of or not aware enough. And there are a bunch of ways that you can get in touch. The first one is you can go to the Julia Slack. There's an HPC channel, #HPC, where essentially all of us here are, available, and obviously many more. Then we have a monthly Julia HPC call. I believe the info last Tuesday of the month is technically not correct. Correct me, Valentin, if I'm wrong, but it's about correct. Let's put it that way.
It's the fourth Tuesday.
It's the fourth Tuesday of the month. Okay, so that's the precise definition. In any case, if you click on that link, right, there you will always find the correct calendar entry. And lastly, and perhaps most importantly, at least in this week, we have a Birds of Feather session on Thursday coming up, which will be much more focused on discussions, as is the nature of these BOFs. So Thursday, 4:30 p.m. UTC. So you have to convert it to your local time zone. And we also put the pre-talks link here. So it would be super cool to hear back from some people who attended today, get some input, even more questions, and hope to see you there, guys.
So one thing I want to add is Alan Edelman, he had a question, right? And for everyone, it says, Julia has so much great parallelism that it becomes a problem for teaching parallel computing. The students are confused what to use when. Should this be solved with higher level blocks, documentation, etc., or through higher level interfaces, or both? I'm just throwing this question there from Alan.
I mean, one part of the question or part of the answer we already discussed in our monthly call, right? And that is to basically we need to provide a better entry point for people to, navigate around in the Julia parallel, Julia HPC, whatever you want to call it, universe. And there's something in the pipeline, technically, you can already find bits of it, but I think at some point when everything is polished, we will, send out an announcement of some kind for a new website that hopefully will serve as such entry point and even more. But on the technical side, maybe someone else will want to comment. Yeah,
and I would like to say there was a question at some point about how to contribute to the HPC community in Julia. Mm-hmm. And if you're interested in, as an example, on working on resources for teaching and highlighting the progress, reach out to one of us. I think that's one of the most impactful contributions one could make.
I want to provide my own perspective in terms of the question. I think for HPC, there is a lot of benefit to teaching a diversity of approaches. And so I think Julia is a great example of a language that provides you with a lot of different approaches to parallelism, all within the same language. And so if you're looking for what to teach first, I don't know, but I think users encounter the biggest problems in HPC when the hardware doesn't match their approach to parallelism. That they are, when the hardware doesn't match the approach that they're familiar with, and therefore you should teach. Excuse me.
I'm very sorry to hear, Johannes, you're having some issues.
I'm sorry.
No, you're fine.
Anyway, really bad timing. So I think you get the point, though, right? Like, hardware is diverse, approaches are diverse. Things are only going to get more diverse in the future. So we need to make sure that people are capable of thinking in different ways and capable of using those.
All right. So I don't see any more questions popping up that have not. Oh wait, there's one last question. Maybe we can take this one. What tools or practices are available for beginner HPC users to debug Julia parallelization errors? For example, you should be using everywhere here. You didn't allocate enough CPUs, causing a seg fault, etc., etc. So tools or practices for beginner HPC users to debug Julia parallelization errors. Any experience here in this group? Who maybe someone who can share some of their own experiences.
So I got this question recently, and I wrote a fairly lengthy reply on Discourse about the uses of as an example of like add everywhere, because I've seen in the past that this becomes one of the most often occurring errors in writing Julia programs. If you're using distributed.jl or even MPI.jl, right, what you need to keep in mind is that you don't not just have distributed data, but you have distributed program state. And so you're doing package loading on each process that you started. And so with MPI.jl, it's kind of nice because the package loading is happening on every process, as long as you don't have any control flow that depends on the rank of the node. Now, on distributed.jl, that's not the case. Right? Distributed.jl is a little bit more flexible. It allows you to start processes after you've already done some work. And I've seen often enough that one of the biggest issue people run into is that they set up some state on the primary node and then start a whole bunch of other nodes, send over work, and then wonder why the state is mismatched. And it's not the data state, it's the state of the runtime on the other side. And so I can try to find a link to that Discourse article, but I basically described my workflow to make sure that I don't encounter these kinds of issues by separating out what is the program, what is the runner for the program that needs to set up all of the distributed states. And so, as an example, I want to minimize the use of @everywhere because it lends itself to these kinds of issues much more. So you often will hear me say that one of my least liked features in Julia is @everywhere, because it is very handy, but it also can turn into a rather big shotgun.
Well, I just want to add something very quick, because I see a lot of great talks, and one best practice, and this applies to any language, right? Don't reinvent the wheel. Try to use optimized packages that people here, for example, have put a lot of effort, right, to tackle that. So that will be a first piece of advice. I see that a lot in some of the libraries that we work on, and just use BLAS or cuBLAS if if you can, or CUDA.jl, MPI.jl. Don't reinvent the wheel.
Maybe a final comment, which sort of avoids the direct question, but hopefully is still helpful, and that is don't scale up too quickly. Don't take shortcuts. Go in steps. A common mistake in parallelization is that your serial code hasn't gotten as much love as it should have gotten, right? So then errors they should have unfold right at the right level. So once you go parallel, you should better be sure that the serial aspects of your code, they are not causing any issues, right? So go in steps. Don't scale from 1 rank to 1,000 ranks, but just go in steps, and that I think makes debugging easier as well.
Mm-hmm.
Thank you very much, Carsten. I think these are excellent closing words for this mini symposium. Don't go too fast. Don't try to debug your serial problems when running on 100 or 1,000 cores. That is true for any parallelization effort in any language, I think. Thank you very much again, everyone present here, for joining today, for presenting your work, for putting in the effort to also answer the community questions. Before we go out, I will put up the slide again with the links to the Julia community, and also to the Birds of a Feather session, which will take place the day after tomorrow on Thursday at JuliaCon, and where I hope some of us will be present again, and which will be a great opportunity to also get in touch more with the people and ask some live face-to-face questions. Thank you very much also, William, for co-organizing and co-hosting this mini symposium. Do you want to add something, William, as some closing remarks?
That I'm just very proud of this community. I really enjoyed the interactions. One of the things that I tell people, like one of the things I'm proud about, is that I might be one of the oldest, if you not consider Alan or Jeff, and that tells you something, right? That there's a new generation, new wave of people trying to do, solve the problems of the past, and I think that's how we should start seeing the Julia, right? As an investment in your wider portfolio, right? So
yeah,
thanks. A pleasure to interact with all of you. So thank you very much.
All right, everyone. Then we're off for tonight. Have a nice day. Have a nice evening, and hope to see you at JuliaCon again.
Great job, Michael. Thank you.
Bye.
Bye.
Great, everyone.